Alrighty, welcome back to operating system. So today, more locking. So this should be one of the final kind of hard lectures. After this, we have parallelization example, and then it's smooth sailing till the end of the course pretty much. So joy, we have overcome the giant hump in this course. So to first relate it to other languages, there are something you might hear called monitors, and now we can explain what they are. So monitors are sometimes built into other languages, and because object-oriented programming became so big, every developer wanted to use it for everything, even though it didn't make sense. So what they devised is an easier way to use locks for object-oriented languages. And how they do this is, well, they allow you to mark a method as monitored and then let the compiler handle inserting all the calls to lock and unlock and creating the mutex for you. So basically all it does is if you have at least one monitored method, it will automatically create a mutex for each object, and then the compiler will insert lock and unlock calls for you. So if you have the unfortunate displeasure of using Java, the synchronized keyword is an example of a monitor. So in Java, let's say we wanted to create a class that represents a bank account. So each account has its own balance. And then, well, maybe if we have a method for deposit and withdrawing, that would be like balance plus equals some amount. So that might have a data race in it if we don't protect it with a mutex. Well, in Java, we can just say, hey, it's synchronized. And what the compiler will do is any synchronized method, it will just insert a call to lock at the beginning of the method and then a call to lock at the end of the method. So basically, this will make sure that between all your synchronized methods, only one of them can be running at any given time. Therefore, you will not have a data race. But of course, the more things you mark as synchronized, the slower your program goes because it serializes. You can only have one of each method per object going at any given time. So this is basically what it does, and it just uses a single lock. There's no using multiple locks or anything like that. So this is what Java will do. So just so you know, it might come up in other things, but basically it just uses a mutex. So there are other types of synchronized or ordering primitives for synchronization called condition variables, and they are actually exactly equivalent to a center for. They just behave a little bit differently, and it's a bit easier to use if your condition is very complicated, or if it's just not a single number, like I just want a certain number of threads to go. Basically, what a condition variable is, how I like to think about it, is it's this pthread_con_t type, and it's basically a queue. So it's basically a queue, and you can put a thread to sleep. You can make a thread go to sleep and then have another one wake it back up when it changes some value. So you have to initialize it, like you have to initialize locks. So there's pthread_con init, there's a destroy, and then, well, let's skip ahead to the wait. So what the wait will do, you'll see it's actually paired with a mutex. So it's assuming you won't have data races, so that mutex will probably be protecting some variable that gets changed. And also the way you can also think about it is, well, if it's adding itself to the queue, we don't want any data races with it adding itself to the queue, so it needs a mutex for that as well. So with this wait call, you have to have already acquired the mutex in order to call wait. And then there is a timed wait. If you don't want a deadlock or anything like that, that will return if something doesn't actually wake you up. And how you get woken up is another thread has to call signal. Signal will wake up the first thread in the queue, and broadcast will wake up all the threads in the queue. So again, easiest way to think about that pthread_con thing is it's a queue. Wait will add this thread to the queue, put itself to sleep, and then signal will wake up one thread in the queue. Broadcast will wake up all the other threads, and we'll have examples of that today. So, like I said, it must be paired with a mutex. Any calls to wait must already hold the mutex. Signal and broadcast, they don't matter. You don't have to have the mutex acquired for those ones. And why, again, like I said, think wait needs to add itself to the queue safely without data races. So you need to give it the mutex as an argument. Also, before the thread goes to sleep, it needs to unlock that mutex so another thread can make progress, because while this thread is putting itself to sleep, it should give up the mutex, so it needs it given by a pointer so it can actually unlock it. And when it wakes back up again, it will try to reacquire that mutex. So you have the lock before and after the call. One mutex can also protect multiple condition variables if you want. And for this course, we'll only consider calls to wait and signal and just ignore broadcast for now. But I mean, broadcast isn't that much more complicated. So again, wait does not have any data races, so you should understand what wait does. This is not the system call wait. This is the condition variable wait. So the thread that calls wait, it will go through 3 steps, all atomically. So it will add itself to the queue for that condition variable. It will unlock the mutex, and then it will block itself so it can no longer be scheduled to run until something wakes it up. So when something wakes it up by calling signal or broadcast, what happens to that is it will get unblocked so it can be scheduled to run again. And then before it returns from wait, it will try to get that mutex again. So it won't return until it has that mutex acquired again. So it will only return from wait when it has acquired that mutex. So if we wanted to change our producer-consumer example from the last lecture to use condition variables instead of mutexes, instead of semaphores. So before we had a semaphore for tracking the number of emptied slots and the number of filled slots. Well, if I was to use it, like solve this using condition variables, instead of that, I need 2 queues essentially, one of threads waiting for filled slots, one of threads waiting for emptied slots. And then my condition would be like just figuring out the number of filled slots there currently are. So initially, there would be 0 filled slots, and I also need a mutex to protect any accesses to that integer that I'm keeping track of the number of filled entries, because we're going to check it and we're going to set it. So in the producer, now instead of having a semaphore wait and then a post at the end, I acquire the mutex that is always protecting this n filled variable. So acquire the mutex, then in a while loop, I can check, hey, is the number of filled slots equal to n, or the buffer size, aka is it full? Is every slot full? If every slot is full, then I should wait for an empty slot to happen. So I add myself to the queue and go asleep, and this is how you would use it. It would unlock the mutex and put this thread to sleep. If it wakes back up again and then this is false, so there is a empty slot, then it can go ahead, do the fill slot stuff, and then increment the number of filled slots. So we just add 1 to it. This is okay. It won't have any data races because we have this mutex acquired. Then it could signal any thread waiting for a filled slot, since it just filled up a thread, and then unlock. Then similarly in the consumer, well, it would lock the mutex, and then my condition is the opposite. If the number of filled slots is 0, so if they're all empty, I need to wait for a filled slot. So I put this thread to sleep, waiting for a filled slot, and then if it wakes back up again and the number of filled slots is not equal 0, then I can go ahead, empty a slot, decrement the number of filled slots, since I just emptied one, signal any of the producer threads that are waiting for an empty slot, and then unlock the mutex. So questions about this? So for this example, is it clear to write it as a semaphore or a condition variable? Who likes what? No opinions? I don't know. This might be a bit more clear for the condition variable one or than the center for one. For this example, doesn't really matter. I would argue the center for one's a bit less readable because the initial value really matters. This one, you know, everything's kind of contained in the code right where it needs to be, so this might be a bit easier to read, but there is an equivalence between center-fors and condition variables. You can always write one in terms of the other, even though, you know, sometimes it might just be really messy and it just comes from using experience. Basically, if it's something simple like just a number, you can just use a center-for it. If it's something more complicated or you have multiple threads going on, it might be clearer to just use a condition variable. So, for condition variables, let's see if we can come up with examples where bad things happen. We always like data races and things like that. So, let's assume I have the following code here, and this will get into our data races. So, with this following code, let's assume we have two threads. We have thread 1 and thread 2. In thread 1, all it's doing is just checking, making sure that a condition is true, because the way you kind of use condition variables is the line right after the while loop. It should always be the case that this is always run when, in this case, condition equals true. So that's how I would like it run, and I have thread 2 that actually changes the condition, a Boolean it created to true, and then signals any thread that is currently waiting for the condition to turn to true. So let's assume, yeah, I have a variable, a Boolean variable called condition. This could, of course, be whatever you want. I will just keep it as a simple Boolean, just for clarity. So let's assume initially that condition is equal to false. We have two threads executing. Thread 1, again, would be starting here. Thread 2 would be starting here. So my question to you, is there any issues with this code? And I will give you a hint. Is there any condition where a thread, in this case, thread 1's the only one that will go to sleep? Is there any case where thread 1 will go to sleep and never wake up? So, only need thread 1 and thread 2 and then interleaving between two threads. So I will give you like a minute or two to look at that and come up with a bad scenario. So is there any scenario between executing thread 1 and thread 2 such that, well, in this case, thread 1 goes to sleep and never ever wakes up again or gets comatose? Yeah?
When you go to sleep and never wake up, if you run that condition, if you check the condition in thread 1, then run everything in thread 2 and then come back to thread 1?
So you're saying I run thread 1 first? So with these, always just think about line by line which thread runs first. So thread 1 runs first. Yeah. So here also in my margins, I'll write out, so there's a condition variable which is basically a queue. Assume it's initially empty, so I'll just write it as a list. And then we also have a mutex, which is initially not held by any thread. So I'll just write it as like a null set. So bad interleaving. So thread 1 goes first. So if thread 1 goes first, it encounters pthread mutex lock. Can it get past the lock call? Yes, because, well, it's currently unlocked. So thread 1 would acquire that mutex. So thread 1 now has the mutex. It would pass this line. Then you're saying thread 1 executes again. So thread 1 executes again, checks the condition. The condition is false. So not condition means, well, that's true. So it goes into the while loop. So do we want thread 1 to execute again? No. Okay. So then we context switch right before we call wait, right? So if we context switch right before we call wait, what would happen is thread 2 executes, changes the condition from false to true. And now what? Thread 1 executes or thread 2 executes? 2. So if thread 2 executes, it calls pthread con signal, which will look at the current queue, which is right over here. The current queue is empty, so it's not going to wake up any thread. There's nothing in the queue. So that will do nothing. And now thread 2 is done. So only hope is to switch back to thread 1. Thread 1 will call wait. So as part of wait, what wait will do is it will put this thread into the queue. So now thread 1 is in the queue. And it will also give up the mutex. So now it gives up the mutex. And now who is going to wake up poor thread 1? No one, right? Now thread 1 is stuck forever, and it's not going to make any progress. Everyone get that? Yeah? Yeah, so part of the wait, it will put itself on the queue, give up the mutex, and then if it gets woken up again, it will reacquire the mutex before it returns from wait. Yeah. So everyone get that? All right, fix it. So here, I will reset. I'll give you another minute to think about what we need to do to fix this. So the condition, it goes back to false. And we reset both of our threads. So thread 1 is here. Oops. Thread 2 is here. All right, what's our fix? Yeah. Yeah, so essentially we had a little bit of a data race with changing our condition variable, right? So we should probably do, right before it, we should probably lock the mutex. And then after, I should probably unlock the mutex. So should I put the unlock here? Let's use a different color. Should I unlock the mutex at option 1 or option 2? Option 1. Anyone disagree? Would option 2 be bad? Doesn't matter. So option 1 might be the better one, but just for fun, let's just put it at option 2 just to show that nothing will go wrong. So let's put it at option 2 so it looks like that now. So we'll do the exact same thing that caused us to have a problem in the first place. That was thread 1 executed first. So now if thread 1 executes first, okay, it hits pthread mutex lock. It can go ahead and pass it because it could acquire that mutex. So now we could say thread 1 has the mutex. Now it could check the condition like before. It's equal to false. So it's going to go here and it's about to call wait. Now, if we switch back over to thread 2, which is where we had a problem before, what can it do? Nothing, right? It hits mutex lock. Well, thread 1 has the lock. It cannot acquire it, so it can't make any progress. So we have no other choice this time but to go back to thread 1. So if we go back to thread 1, then it would call this wait. What wait will do, again, it will put itself in the queue and then give up that mutex. Now, the only choice is to run thread 2. So thread 2, it locks that mutex, so it can now successfully lock it. So now thread 2 would acquire the mutex, change that condition from false to true, and then next thing it would do is signal. So what signal will do is wake up thread 1. So it will remove it from the queue. And now thread 1 can execute. If we chose thread 1 to execute at this very second, it would try to acquire that mutex before it returns from wait. In this case, it will not be able to return from wait because thread 2 has the mutex. So in this case, it won't be wrong. You might argue it's a little bit inefficient because I just woke it up while I had the lock and it didn't have any chance of acquiring it. So you can argue that maybe it's a bit better to put the signal after the unlock, but it's not incorrect. So in this case, it wouldn't be able to make progress because thread 2 still has that mutex. So only choice is to execute thread 2. Thread 2 would finally unlock the mutex. So now the mutex is not held by anything. And then, while we'd execute thread 1, in order to return from wait, it would have to reacquire that mutex, currently not held by anything. So thread 1 will now have that mutex, and it is now done with that wait call. So now it's going to check that condition again because it's in a while loop. Oh, okay, that condition is now true. So the condition's now true. It will fall through and then execute this line. And it's running while the condition is true. So everyone okay with that? All right. Question I always, well, most of the time get asked is like, hey, isn't that while a bit inefficient? Would this work? Whoops, didn't mean to draw a line across the rest of it. There we go. You think so? No? Okay, give me an example of it breaking then.
If you signal thread 1 to be awake, but it's still, but you haven't unlocked the mutex yet, like the situation we had before where it wait again, but because it is a while loop, it just went to sleep again, right?
So you want thread 1 to execute first and put itself to sleep?
Yeah.
Okay, so let's do this again. So thread 1 executes. It would acquire that mutex. So thread 1 now has the mutex. Checks that condition. The condition's false. So it would put itself to sleep and give up that mutex. So we have now put ourselves to sleep and given up the mutex. So thread 1 is now taking a nappy nap. So now thread 2 executes, you said. So thread 2, it would acquire the mutex. Okay, and then change that condition from false to true, then signal. So signal would cause thread 1 to wake up. And now what?
Thread 1 just tries to get the mutex, but it can't.
Yeah, thread 1 cannot get the mutex right now, so it can't return from wait. So I have no choice but to execute thread 2, right? So thread 2 would unlock that mutex. And then, well, thread 1 can now acquire it and return from wait. Oops, that's supposed to be empty still. So thread 1 can now acquire it and return from wait. And doesn't, since it's an if now, it won't check it again. Runs this line and the condition's true. Seems fine. So if okay, some of you are questioning, giving weird side eyes. So in this example, assuming that this is all we're doing, it never changes back and forth, writing an if there will not matter. But this is a very, very, very special case, because likely what will happen is your code will look like this. That condition will constantly change between threads. So here is another version where I have 3 different threads. So let's say, again, I have the bool condition. We're going to do that. So I have that bool condition. It's initially equal to false. I have cond, which is currently empty. And then I have my mutex, which is currently unlocked. So let's say, and we have 3 threads. So here in thread 2, right, it has our improvement where we lock accesses to writing that condition, so we don't have any data races. And we also have thread 3 that locks it as well. But thread 3 is now going to change that condition to false. So since it changed it to false, it doesn't need to signal anything, right? Because it just set to false. The condition we want to happen in thread 1 is this line should only execute, only run if, actually here, if condition is true. So something really bad that we do not want to happen is that line executes while the condition is false. So given this setup, is there any interleaving between threads 1, 2, and 3 that occurs such that something bad happens? So I will give you another minute to think about that. And again, with all these, just assume interleavings between threads. Threads just execute one line at a time. Don't try and jump ahead too many steps. Just pick one, run a line, pick one, run a line, pick one, run a line. So what you want to happen is thread 1 executes first. Okay, so thread 1 executes first. Oops, we didn't update the cond yet. So thread 1 executes first. It hits that mutex lock. It is the only thread. Well, it's the first one there, so it acquires that mutex. And then at this point, well, thread 2 can't run any more lines. Thread 3 can't run any lines because they try and lock the mutex. So let's run it until completion. So if not condition, so is the condition equal, what's the condition? It's false, so it's not, so we'll go into here. We'll do wait, so what wait will do again is add this thread to the queue. And then give up that mutex. So now this is what we look like. So now what happens? Yeah. So thread 2 goes next. So if thread 2 goes next, it acquires that mutex. Huh? Oh, thread 2 or thread 3? I'm saying 2. All right. Votes for 2. Votes for 3.
Like you want it to like mess up, right?
Yep, we do want to mess up. All right, majority rules, 2-1. So let's see what happens with 2. So 2 goes. All right, so it changes that condition equal to true. So the condition is now true. And then it unlocks that mutex. Now what happens? Thread 3, yeah. So if I wake up thread 1, what will happen is I will wake up thread 1. Yeah, thread 1 could get the mutex, but just because it's woken up doesn't mean it will immediately acquire that mutex. So sure, maybe I did wake it up, so thread 2 woke it up with the signal, but doesn't mean it's going to return from wait. Either thread 1 or thread 3 could acquire the mutex right now. Thread 1 acquires the mutex right now, we're all good still. We'll run that line with it equal to true. But if thread 3 acquires that mutex, well, then we are a bit screwed. So thread 3 acquires that mutex, sets the condition, whoops, I stole too much. Come on. So sets the condition equal to false. Then unlocks that mutex. Now thread 1 can actually acquire it again. Then it would return from wait, and since it's not in a while, it will just fall right through, and then it executes that line while the condition is false, and we have now broken everything. So the moral of the story is if you have something like this, and even if you argue that I could write if instead of a while and it will be better, it will still work, that might be true at some point, but most code looks like this and keeps on changing it. So your assumption may not hold ever, and if you don't change this from an if to a while after you change your assumption, then you will have a bug where you will never, ever, ever be able to fix it until like 7 years later. So the moral of the story is no matter what for these, just write while because you might need to check that condition again. And there is also other reasons why you might need to check that condition again. In some implementations, even if you put yourself to sleep, it can just randomly wake you up even though no one has signaled you. So it might even be, even if you could argue that if is okay, it might not actually be okay, and a whole host of other reasons. So just put it in a while and always recheck that condition. Yeah, other things, let's see. Yeah, if we back up to, yeah, thread 3 executing next would not have broke it. All right, so everyone okay with this? Yeah.
So if we go only one and three, is it like one shouldn't ever wake up?
So if we go, so skip, like if we reverse all the way, let's say we have, oops. So let's say the condition is false. The mutex is currently not held by anything and thread 1 is asleep. So you're saying, is anything bad going to happen if thread 3 executes next?
Like it shouldn't, and nothing bad should happen, but like there's a chance one can still wake up just without a signal.
Yeah, in some implementations, thread 1 could just randomly wake up. It's kind of fun. But if thread 1 doesn't randomly wake up, then if thread 3 executes next, right, it will acquire that mutex. Change the condition from false to false, doesn't matter, and then give up the mutex. And then at this point, we're the same situation as this, right? Doesn't matter, it's going to work. Even if it's assuming it doesn't randomly get woken up, which again can happen in some implementations. But yeah, should be safe as long as you assume something sane. Yeah.
So if you were to like go through all of like thread 2 stuff and then thread 3, would you have the same issue with the wait? Like you'd always be like you'd be stuck at it would never be signaled to.
So in this case, since we're protecting everything, there's no like lost wake up like we had before or anything.
Because like if you were to go through a thread 2, but if you were to like I don't know, like if you were to you lock it and
So if thread 2 executes now, right, it would acquire the lock. Set the condition from false to true. Then give up the lock. And then signal, right? And signal will just wake up thread 1. So if thread 1 didn't run yet and it was still at the beginning, then it wouldn't have been in the queue. Signal just wouldn't have done anything. And then if thread 1 runs at this point, it could acquire that mutex, check the condition. If it's true, it would just skip over here and execute this line.
But if you did like all thread 2 and all thread 3 negative thread 1, like would it then be stuck in the wait? Like you have
Oh yeah, I see what you're saying. So yeah, if I went really, really fast, I could just, let's say, yeah, there is a scenario where something, goes to sleep and doesn't come back. So if thread 2 executes all the way, it just updates that condition equal to true, signals nothing that is in the queue, and then thread 3 executes all the way, sets it back to false. Then, yeah, now if thread 1 executes, locks, checks the condition, waits, and in this scenario, if these are all our threads, it will get put to sleep and not wake up again because nothing will signal to it. But in real programs, there'd be lots of versions of thread 2 waking it up over and over again. If this was your actual program, and you want to make sure you actually woke up after some time, that's when you would use like this timed wait if you get into that scenario. So you can wake yourself up after a certain bit of time. Or you might have something that like broadcasts and wakes up everything just in case to unblock things. All right, everyone good with that? Yeah.
Would this be an application that would
like, how would I use this for ordering, basically?
Like what I'm saying is if the issue here, like one potential issue is if thread 2 and thread 3 run before thread 1 and we get stuck in the waits, like infinitely, would we want some type of ordering here, such that thread 1 goes into the wait beforehand?
Yeah, so the question is, wouldn't we want some type of ordering here so it doesn't do that?
Yeah.
Depends on your application, depends what you're doing. Just depends. So some things you might get into the case where like the last one doesn't run because there's nothing to do or something like that. But this scenario, like just having 3 threads doing this is a bit strange, where they only run once. They'd run multiple times while there's still a bunch of work, and an actual scenario would be doing a lot more than just 3 threads. We're just using this to illustrate that bad things can happen. Alrighty, so all right, still good. All right, so a little bit of, I guess lab 5 got delayed, but to talk about that content. So locking granularity is the extent of your locks. So you should use locks to prevent data races, but if you lock large sections of your program, you serialize the whole thing, and then it just becomes slower, possibly slower than just not using threads and locks at all. So for performance, usually what you do is you divide locks into smaller sections, so you protect only as much code that needs to be protected. Maybe you need to create multiple mutexes instead of just one. And you could imagine like, hey, if I want to parallelize a hash table, cough, cough, you're doing that in lab 5. I'm giving you the hash table, you're just adding lock calls. So you have to add like 5 lines of code. So lab 5 is short. So you do not get the extra thing where you implement your own semaphores. So you're welcome. You just have to add essentially 5 lines of code-ish. So things to consider about locks is